Hi, everyone. So we just want to spend a little time kind of going through pipelines at maybe a little bit more granular level of detail and kind of get into some concrete examples. So hopefully this video will be useful. I'll kind of step through the different pieces that we think are particularly important for kind of pipelines and really some examples of how we think about them and just some maybe gotchas and things to watch out for as you're continuing to build yours out and refine it. So we'll jump right in, just kind of as a reminder, right? We have these problem settings that are mostly kind of temporally validated. And so we have, some history of training examples, some window of time that we have to reserve for labels, and then uh, another set of time for picking up examples for validation and then another window for labels. Something that's kind of easy to uh, get confused about or mix up is that as we're kind of thinking about, restricting these periods of time, the features can go back further in time, right? So feature data can go all the way back. Features uh, during the validation examples can pull from the window of time that overlaps with training and even beyond that, because that's kind of all fair game. It's all history at that point in time. Um, the things that are important, of course, are that the examples don't overlap with the labels, and of course that you are always looking backwards in time for features, imputation, scaling, anything like that might be a source of leakage. So as we're thinking about kind of splitting things up, we want to figure out when these cuts in time are, but we don't necessarily want to um, split the data immediately, because then we might kind of artificially limit where we're pulling our features from. Um, so the first bit of the pipeline is really kind of figuring out where those splits in time are, and then that flows into our label definitions are all kind of relative to those splits. Our feature definitions are looking back from those. So that's why we put this up front, both because of kind of leakage concerns and also because of flexibility. You don't know a priori when those splits will be for any given project that you might want to use your pipeline for. So once you figured those out, then you need to figure out your cohorts, right? So if we're thinking again about this crowdfunding sort of example that we've used a few times, uh, your cohort might be logic about we're only going to focus about projects in certain geographies, or maybe at schools with a certain history. Maybe we're really concerned about projects where it's the first time a teacher is posting something, or a school is posting something, or projects from districts that have lower or higher poverty rates, or things like that. So we need to kind of go from what the splits we'll be using are to exactly what the entities and at what point in time we're focusing on. So pulling data from the database and then kind of pushing this sense of the cohort, so an ID at a given point in time, back into the database. Um, then we want to append on the labels for those entities at those points in time, using that label definition and the relative window. And then appending onto that, we want to add on the features. And so now we've kind of constructed all the things that we're going to need for our matrix. And at that point, all we have to really do is join all those things together, and then we can create train and validation matrices. And then now once we have train and validation matrices, of course, we can go and train our model using the training matrix, and then using that resulting model object, as well as the validation matrix, predict scores the um, on the validation, the entities in the validation matrix, and then once we have those scores and the known actual labels from our validation set, we can evaluate our models, and then of course downstream do model selection and think about deployment and all of that. But in terms of kind of the core machine learning modeling pipeline, this is kind of the main piece. And of course, this is assuming that you've done some ETL and whatever sort of data pre-processing and cleaning upstream. and then of course all those other pieces downstream. But this is really just the core bit that you're probably working most on right now. Um, to run all these things, right, you need to um, have some kind of wrapper function, your pipeline runner or orchestrator that runs all of these in order and feeds in configuration parameters that are coming maybe from some sort of YAML file, or it could be a text file, Python file, something else. But all the kind of project specific stuff really lives in that YAML, and everything else here is basically project agnostic, right? You should be able to take this and use it for any other project, right? Ideally, at the end of the semester, we could take the code that you've built, have everyone swap projects around, and you just write a new config file and hit go, and all your code should kind of translate over. And then just to kind of highlight, right, these first bits where you're really working with the data and munging it and doing features and features, labels, cohorts, things like that. The database is well tuned for that sort of work. And so that'll be more heavy on kind of templated SQL with Python. We talked a bit in one of the previous tech sessions about some best practices and kind of tips and tricks for doing that. So you might look back to that tech session if that's helpful. And then of course, as you actually do the machine learning, the prediction, the evaluation, that's going to be more heavy in Python, storing artifacts back to the database for metadata, maybe the trained models to disk as well. So then you can use them later. One, kind of pointer is that we do usually say, right, try to store all your intermediate products, so that way if you say want to just add one more feature down the road, well, you can pick up everything up to the feature creator, add that one feature, and then go through the end. Or if you want to look at different evaluation metrics, well, if you've got your scores stored or your model object stored, you can pick up from that point in time and just do the last pieces. So it'll save you a lot of time, and of course we can always um, find disk space, or push things up to S3 where there's plenty of space that is pretty cheap to store. So we like to try to kind of keep as much of the intermediate products as we can, just in the interest of saving ourselves time down the road and not having to rerun the entire thing every time we want to make one small change. So the pipeline runner piece itself can actually be very, very simple, and each of these pieces should be or can be pretty simple in their own right. But the runner, right, is really just kind of orchestration, matching configuration parameters to each of these functions and running them in order. So here's a perfectly reasonable functional example of that, right? Import all of the other pieces in your pipeline from the relevant files. And then basically just have some function that says, okay, do the splits. Now I've got my splits, feed them into the cohort generator, feed that into the labels and feature generators, and then iterate over those splits. Figure out what my model grid is, again, coming from some sort of configuration, iterate over each of those model specifications, run the model, predict scores, and evaluate, storing the results to the appropriate places. So the runner itself can be no more than, what is this, 30 some odd lines of code, something like that. And I mean, of course, this isn't well commented or anything just to fit on the screen, but you can keep this, or should be able to keep this, pretty simple, and all the kind of complexity of the problem itself will be kind of outside in configuration, and that will get a bit more messy, and I'll talk through an example of that a little bit later on. But first, I kind of want to step through sort of each of these pieces and think about kind of what are the inputs, what are the outputs, and maybe some pointers that might be helpful. So let's start with the time splitter. We already kind of mentioned this at the top, right? We're working in this temporal context, so we have to kind of figure out what are the points in time for the training examples, for the validation examples, and then of course do this, iteratively for each training validation set. We tend to draw these out starting from the earliest time and moving forward, just because that's kind of a natural way to think about things. In practice, one kind of tip here is it's usually best to actually start the calculation from the end and move backward in time. Really, because um, if your windows sort of don't, like if the amount of history that you have isn't evenly divisible by the relevant windows, you'll end up with some, small gap. And you'd rather have that gap be at the end of your data set and the oldest, kind of least relevant data, than at um, the beginning of the data set, or rather at the most recent point in the data set. So we usually start at the end and calculate the cuts backwards. Uh, so, what does this need as inputs? Well, it's, those temporal parameters that we've been asking you for in some of the update assignments, right? What's the beginning of time? What's the end of time? As far as examples and labels are concerned. What's the window that you're going to use for labels? So how much buffer to put in between the training and validation sets and the validation set and the end of time. What is the history that you're using for examples? So how big is the training set? Often we actually think of this as kind of the maximum history. So maybe that training set, like we have up here, right? The training set is expanding because we're going all the way back to a certain point in time. But you could also think of it as a fixed window that's shifting back as well. And then what's the update frequency for the models? So, how far are we shifting forward between each of these lines here? And as I mentioned at the top, the output here is really just sets of pairs of dates. It's a bunch of tuples, not splits of the data. So you're not actually chunking up the data at this point, because then when you go calculate the features, right, you still want to be able to go back further in history. But you need to know when those when that training period starts and stops, or if there are kind of other samples within it, when those are, when the test period starts and stops. So then you can figure out what's the cohort at that point in time, what are the labels extending forward from that point in time, what are the features extending back from that point in time. So once you have those temporal splits, the next piece is figuring out what your cohorts are. And so here, right, you really just need the split dates, whatever logic you're using to define your cohort, and whether that is kind of everything that's active at this point in time, or you're focused really on a certain subset that you actually care about modeling. And often the easiest way to do this is kind of, well, you could store all that logic as basically just a snippet of SQL in your configuration file, and then that SQL gets run, or it could be a separate SQL file or something like that your configuration file points to. But that way, all the logic is kind of relative to your particular project is stored somewhere else, but you're going to spit out just an entity ID and a point in time or a date for each of these entities that are in the cohort at a given point in time. And then that, combined with the train validation split dates, gives you the relevant sets that you'll use to build your matrices. And then, of course, as an input, you need the data that you've done any sort of cleaning and ETL on to start with. So great, now we've got our splits, we have our cohort, and we want to append onto that our labels. Well, this is going to look a lot like the previous step, right? We're going to need the split dates, we'll need the cohorts, and then we'll just need the label definition, whatever logic, whether that is for the crowd funding projects, did they get funded within did they meet their fully funded criteria, say within 3 months or within 6 months or within a year? Did or maybe you're label definition is, did they get within 90% of their funding? So there's some logic that's going to be relevant there. And then there's a window in time that you need to integrate that logic over. And so you'll again want to store all that kind of project specific logic and configuration, temporal parameters into configuration, and have the downstream methods be kind of agnostic of that. So you can use them again and again for whatever projects you encounter. And then of course they rely on the clean data. And so now, we're going to get another table of data out that just has entities, dates, or times, and then labels. Potentially, right, at this step, you could create, multiple different labels if that was something that you're interested in exploring kind of differences across, for instance, like we were looking at with the healthcare paper earlier on when we were talking about analytic formulation. And so you could make this a table with many different label columns that you then iterate over in your downstream modeling, or you could just have this be a single label column, and then different iterations of that would be different kind of runs of the modeling pipeline. So great, we've got splits, cohorts, labels. Now we want to add on our features, and to do that, again, we need basically the same stuff we needed for the labels. And in practice, you could even run these two things in parallel. It's just easy to show them in a kind of linear flow in the pipeline. But we need the splits, we need to know the cohorts, and then we need a bunch of logic for feature definition. And this is where your kind of project-specific configuration is probably going to get much more long-winded in some sense. And so you might have different SQL files for different types of features, or very long configuration. And then windows of time relevant for all those features. Are we looking at, the performance of projects at the same school district in the last, 3 months, 6 months, year, 5 years? Or are we, looking at the composition of the student body over time, things like that. So you'll need, very, very specific logic for your project. And then, kind of temporal parameters relative to that, and then those will operate on the data in your database. And what this will output is, IDs, dates, and a set of feature columns that will then are ready and prepped to feed downstream into your matrix. So you probably want to do, any imputation and all of that as part of this process. You could think about those as separate components in the pipeline diagram, or all in one, are kind of totally reasonable depending on, sort of how you're implementing those things. One, pointer here that has kind of two reasons behind it is it's often really useful to group related features together. And there's two reasons for this. One is, one thing that is often quite useful is to do some sort of iteration over different sets of features that go into your models downstream. You can really kind of think of the feature set itself as a hyperparameter of the overall kind of modeling process. And if that's true, right, you could say, well, these are kind of all similar sorts of features that maybe have the same cost of collection, right? If I gather a data set that, has this set of features versus a different set of features, or kind of seem naturally related to one another. So you can gather all those together as separate feature sets, and then do something like, leave one in, leave one out types of analyses, and run across those different groups of features together, and look at how those impact model performance. Are there ones that aren't worth including, or are, the model is relying particularly heavy on, or redundant with other ones. So that can be, very, very helpful for kind of refining your models. The other point here is because Postgres, since we happen to be using Postgres here, actually has column limits. So a table, I think, can only have up to something like 2,000 columns. If you have, more features than that. And here, right, of course, think about features as maybe it's one hot encodings of a bunch of different categorical values that are then, aggregated over time windows. So you have, 100 categorical values for this one feature aggregated over 5, temporal windows. And now we've got 500 features. So you want to, think kind of carefully about how big those tables are getting, just in terms of hitting Postgres limitations. And you might want to split things up just for that reason, and then you can join them all together when you pull them into your matrices for actual modeling, which is, of course, the next step. So now we've got all the pieces that we need. We just need to join them together in the matrix creator. So the inputs here, just the splits, the cohorts, the labels, and the features. And we're going to create, pairs of train and validation matrices for this temporal validation process. Those could be NumPy arrays, pandas data frames, CSR matrices, or other sparse matrices, if that's appropriate for your context. So, you at this point have kind of pulled everything together, created your matrices, and really this should be a very simple function, right? It's just joining all those other inputs that you've already kind of calculated, and finding the right cuts for the matrices themselves. So now we can get into the kind of machine learning in sort of proper terms and do our model training. So we just have inputs of a train matrix and model type and hyperparameters, again, coming from some configuration that's being passed through by our kind of orchestration pipeline runner function. And the output here is going to be a model object, but also some metadata about that model. A couple of things to note here, right? One, in principle, this should again be a pretty simple function, right? It's basically just saying, what type of model object do I need to instantiate based on the configuration, create that, run, if it's an sklearn model, run .fit, and generate a model object. There's a couple of other things that you might want to be doing here. One, you want to keep track of all these different models that you're generating and their performance, so you can kind of easily look at those things later. So it's helpful to store back to the database some sort of ID for this model, what type of model it is, random forest, decision tree, neural net, whatever hyperparameters were used in the training, and think there about that's probably also right. Not just the kind of traditional hyperparameters of the model, but it's this model trained kind of using this set of features with these temporal windows, and then the dates over which it was trained. So you kind of want to think about stuffing all of that back in the database for downstream analyses. And then the model object, of course, you'll push down to the scorer functions, but you may also want to cache that to disk as well, so you can pick it up later. That usually think there's something like pickle can be useful. I think joblib tends to work a little bit better with particularly with larger models, so you may want to look at that instead. But the other kind of important pointer here is, right, we're thinking about, I think we've talked about this a couple of times in class, a model as sort of an instantiation of a model type with a certain set of hyperparameters, certain set of features, certain label definition, as trained at a particular point in time on a certain temporal split. But you kind of want to think about those sets of models that all share the same, type, features, hyperparameter, et cetera, as related things. So then when you look at your model selection over time, you can, say, well, this, on those graphs that we were showing in class, right? This one line is a random forest with this depth and this, min sample split, and so on. And this other line is, a random forest with a different max depth and sample split instead of hyperparameters. So you want to keep track of the same kind of specification or type of model as trained on different points of time. So you might have different concepts of model sets and models themselves. And you want to make sure that you're kind of doing that accounting in a good way to make your life easier when you're looking at things later. Great, so we've got, validation matrix, model object. We just need to generate scores. So, again, should be a pretty simple function. Right, will yell at me if I don't remind you. Here you want to use predict proba, not predict. You don't want to assume a threshold of 0.5. You just want to get these, rank order kind of risk scores out that then you can apply different cuts and look at things like the PRK curve down the road. A couple of notes here. Again, it's super helpful to persist these predicted scores. If you're running, large grids over particularly large sets, for instance, like in turnout where you have 10 million or 12-ish million people in your validation matrices, this can get very, very large very fast. So, you may want to make storage optional, especially while you're kind of debugging and iterating on those things, and then only store once you kind of have a first set of refinements. And you also really want to be very, very sure to index that table in Postgres, so retrieving from it is much more efficient. And then the last bit, right, once we have our scores and our validation, like actual labels, we just want to do some evaluation. So here we need, our validation matrix, really just to get the labels and the associated metadata, the predicted scores from the model as applied to the validation matrix. And then, of course, we need, what metrics do we care about? And this, again, is something that you want to be flexible over and provide based on some configuration. So we take, those three things and then really it's just a matter of here, again, we can probably reuse a lot of stuff that's out there, say from sklearn, to actually do those calculations of the different metrics. So we'll take that, and the result will be model ID, the dates that are relevant for that validation, right? What validation set was it looking at? What metric did we care about? Parameters for that metric, such as a cutoff or score threshold, and then what was the value? So have a couple of examples here, right? All on March 14th, 2015. The first row is looking at precision at 500 absolute. So that's, take the top 500 entities as sorted by their risk score and calculate the precision among those. Here, just, 0.62 as example. The next record, right, is looking at recall, taking, sorting by risk score, looking at the top 15%. And getting some value. Or you might look at recall, sorting by risk score, and then taking everything that has a score of 0.8 or above, and maybe that gives you a different value. So you might, want to have some flexibility here in terms of kind of how you think about those metrics and parameters to them and how they're calculated. Again, as with most of the things, right, store the intermediates, and this is actually really kind of the intermediate in terms of going into model selection and whatnot. So you want to push all that into the database as well. One thing, that might be kind of something that you've done in previous uses of machine learning, right, is doing some sort of inner loop of hyperparameter optimization or something like that, and only kind of saying like, oh, and here's the best random forest, here's the best decision tree, here's the best logistic regression, and we're just going to compare those downstream. And we'd actually advise really against doing that here, because we're going to look at kind of more flexible things downstream, right? We want to evaluate different kind of model specifications with different sets of hyperparameters for trade-offs in terms of fairness and accuracy and things like that. So we want to preserve that flexibility, kind of expose all those internal different variations, and kind of have everything to compare against when we're looking at different sort of menus of options that we might put in front of policymakers, because the best random forest in terms of precision at 500 is, likely not to be the best random forest at a different cut of precision, or even at the same level. But if we're then kind of trying to trade off between fairness and accuracy in some way. So that's just one kind of tip to think about as well. So, finally, I kind of wanted to give a brief look at, well, we keep, talking about store this into the database or pull that from the database. Just kind of a very bare bones schema of what some of those pieces might look like. So in your database, you have some raw data that you got for the project. You've probably done some initial kind of processing and cleaning. So you maybe have another schema with a bunch of clean data. And then in terms of the machine learning pipeline, there are really kind of two schemas that'll be particularly relevant. So one is kind of whatever prep you're doing for the modeling. So as you're storing those intermediate pieces, what's your cohort, what are the labels, what are, and then what are maybe different tables representing kind of these different sets of features that you might want to have. So all that for the first piece that's more, heavy working on kind of SQL and getting your matrices ready, and then all these results that you're going to be storing back to the matrix or back to the database. And here I kind of mentioned this idea that you might want to separate some concept of model sets or specifications that share the same types of parameters, versus models that are instantiations of those specifications on a given training set. And so you'll kind of want to be able to keep track of what set does a given model belong to, so then you can look at those performance results across the different training validation sets, and get an idea of what's more performing better in terms of stability, or what's performing better in terms of recent versus historical performance, or just average performance overall. So looking at model selection across model specifications, not across models per se. And then of course somewhere to store predictions and evaluation results, which we kind of gave the schema for above. And so just to wrap up, I also kind of want to delve a little bit into this idea of where all the configuration is coming from, where all the project specific stuff is happening. And I think a good way to do that is sort of by way of example. So here's a URL for the example I'll be walking through. This is a public repo from a project that we've done in the past. And I'll jump over to that here, just so it's blown up and a bit easier to see. So this is an example of what some of this configuration might look like. It may be at a little bit more of a level of abstraction than you really kind of need to build here, and a little bit more flexible. But I just kind of wanted to give you a sense of how we think about some of this. So you might, this is in this case all in kind of one big YAML file. You may even want to think about splitting up some of these different pieces, temporal configuration, especially the feature configuration, that can get very long and very hairy pretty fast, and so you may want to split those up, or move them into different SQL files. Here it's all kind of in line. So we start with those temporal parameters. There are a couple more here than maybe we have talked about, just because we're trying to simplify things. But it's the same basic idea. What are the time periods relevant for where the features start and end? That might be different from where your here we call it label start and end time, but essentially example start and end time. So where how far back do you trust the data in terms of getting features may be different than how far back do you trust the data in terms of getting labels and therefore examples. How much are we updating as we move the model forward? I've kind of skipped some of these as of date frequencies, but that's about sampling intermediate within those windows. And then, what are the label time spans, right? How far out into the window are you looking? So, then once you have those splits, right, you need to define your cohort, right, which is just a set of entities on at different points in time. And a simple way to do that is just, provide here's a bit of SQL that takes, at a given point in time, what are the entities that are relevant for that? And then that'll output those pairs of entities and dates. And then once you have entity date pairs, right, you need the labels for those, and you'll have a bunch of logic that's relevant to your project, and you can just encode all of that in again in a SQL statement. You could, of course, think about other ways to do that, but this is just kind of one simple way, right? You have a date, you have some window of time that you're going to take the label over, and then you have some logic that's that relates to it. In this particular case, it's maybe not the best example because everything that exists in this table gets a 1, and so all our zeros are coming from everything that doesn't exist in that table. That's kind of maybe a bit of an edge case, and then probably not relevant to any of your projects. Well, I guess maybe it's closer to the turnout one, but you still have to be careful about some of the non-votes that are still in that table, the votes table. So you'll probably actually have like something here like a Boolean or something like that that's taken over that time window, and has encodes some logic about what counts as a 1, what counts as a 0. And then the kind of bigger, messier piece tends to be the feature aggregations. And it really depends on what level of abstraction you want to go to. I would say, for the kind of class projects, you probably don't need to go as abstract as we do here, because it will, make your code a bit more tricky on the Python side, particularly. But essentially, right, you kind of always want to say, well, the features. So the way this works in these types of configs, or the configs that we're running, are we say there are kind of different feature aggregations in YAML, right? That this is just a list, so everything that starts with a dash is one set. That's unfortunate. I grabbed an example that only has one, but often this entire block would be repeated a couple of times for different feature aggregations. See if see if I can pull up an example with a couple or with multiple feature aggregations here, just for kind of comparison. That'll take a second to load because GitHub's been slow for me. So I'll kind of go through this and then show that. But so essentially for each given kind of set of features that are related, you'll have where are they coming from, right? Which might be some SQL snippet. What is the date that's relevant for calculating these aggregates, right? The history of project funding at a given district in the last year, 5 years, 10 years, right? What's the date that you're calculating relative to? maybe some logic relating to imputation. Again, this is probably at a level of abstraction more than you're going to want to go to. And then, what are the aggregates that you're going to calculate for those features? And in this case, it's really just doing a count star. And then what are the time years or the time periods that you're looking over? Here we're doing, this is just kind of by way of example, right? You can look back a month, a year, 100 years if you wanted, all time. Hopefully those last two are pretty similar. Let's see if this is loaded to give some more kind of concrete examples. Yeah, here we go. So you might have, in this case, right, we have a group of features that are all about demographics, where we have, this is coming from some entity and a knowledge date, and then we're pulling out from some just big JSON-B, sex, race, age, and so on. And then we're calculating some aggregates of those over these different time windows. Even though you'd think of demographics as, well, aside from age, right, as relatively static, you might have different knowledge of those different demographics over time. And so you still want to kind of think about some sort of aggregation for that information. And then we have another set of features. These are, in this case, MH means mental health here. And so we look at, again, pulling these features from a different place with respect to a certain date. And we're just looking at a flag that we've pre-calculated in that table. So we've already done a lot of the work of kind of figuring this out on a date-by-date basis. And we're just doing, a sum, a max, and an average over that flag. Let's see if I have. Look for something that is maybe a little bit more. Oh, okay, yeah. So here's, how many days has this person spent in jail? So again, some snippet of SQL where the features are coming from. We've basically done some pre-calculation here as well to kind of calculate days in jail for different periods of stay. And then we're looking at that quantity. We realized that there was some problem with the way that these were marked. Some people get booked to have or get sentenced to spend weekends in jail, but then are released on their own recognizance during the week because they have a job that they need to be at. So we realized, we have to kind of deal with those specifically. So we have another little snippet of SQL for how we're doing this calculation, and then taking these metrics. How long have they spent in jail over the last 5 years, 2 years, 1 year, or all time in the history of our data. So hopefully this gives a couple of examples of how you might handle kind of different features and the flexibility. Again, this is probably chopped up and abstracted more than you might want to do for your projects. It would be totally reasonable to have, say, big kind of templated SQL files that specify a lot of those features for you and where they're coming from. And then maybe your configuration is just says, these types of features come from this file, and they should all expect the same sort of parameters, and then your code just fills in those parameters as needed. But you can, of course, do things that are more flexible. You'll want to, maybe isn't too worth kind of spelling out, for categorical columns, you might want to figure out some strategies around, am I just doing a one-hot encoding of every single value and then taking aggregates of that over time? Or are there limited set of values that are actually relevant? Is there some hierarchy, for instance, in the EPA? Right, there are, you know, many different types of violations, but there may be some structure to those, and you can say, well, we're only going to focus on the prefix for the violation type or something like that, and group them that way. Or we're going to take the, you know, 25 most common values of this categorical and group everything else together as an other, depending on kind of what the distribution of that categorical looks like. So you may want to do things like that to kind of limit sparsity, or think about, you know, combining things that are similar and related. And then finally, so actually it's quite a lot of features. So, and then you might want to do, or I mean, and then you'll of course need to say, well, and this is the model grid that we care about, trying to model across. And, you know, one way you want to do this is you're going to have this big hyperparameter grid. You want to try to specify that in a relatively compact way. So something that can be useful there is sort of saying, well, for this type of model, right, we have these different parameter sets that we're interested in looking at. And then what you can do in your code is just take a big cross product of all of these things, you know, create a big list of model types that you're going to explore, and then iterate over that list. So in this case, right, we're running for just random forest alone, 1 times 2 times 3 times 3 times 3 different models. And this is actually a pretty narrow grid, because this is sort of from later in the project where we've already refined it a little bit. And I think in the sklearn video, right, you kind of went through some examples of ranges of hyperparameters and things like that you might want to explore. So I won't dwell on this too much, but it is useful to not have to repeat, you know, right, if we wanted to spell that out entirely, it would be much more onerous. And then finally, right, you also want to say, and these are the metrics we care about. So, you know, in this case, we're looking at both precision and recall at, you know, essentially every percentile in this case, and you could even find a more compact way of specifying that, as well as the top 100, 200, and 500 in absolute, you know, top N, top K terms. So that's kind of an overall tour of just how we think about some of these configuration files in relation to keeping all of our project-specific stuff sort of in one piece that's then read in by the rest of this pipeline that is all kind of agnostic of the project itself. So hopefully that is helpful and kind of a decent overall tour of some of these pieces and how we think about them.